Welcome back. We now are going to begin to talk about issues concerning the fit of logistic regression models. Now, we know that, and we've learned methods to use a program like Stata or any other statistical package to generate the coefficients of a logistic model. But it's one thing to generate the coefficients, and it's another thing to be able to say that the coefficients produce a model that in turn produces a probability that accurately reflects the true outcome experience of the data. This is what we don't know. In linear regression, it's easy to, at least if there's only one independent variable in the model, to simply do a plot. Look at the response variable y versus the predictive variable x. Look at the plot, see what it looks like. If it looks more or less linear and you fit a straight line, that's good. If the plot looks like it's a curve and you fit a straight line, then you know you have the wrong model. Now, in logistic regression, it's not so easy. It's not easy to look at the nature of the relationship as easily as it is for linear regression. So what we have to do is we have to figure out some methods to determine whether or not the model that we generated is a good fitting model. Now, I want to mention that this issue of whether the model produces good probabilities is really only important in a type of model where the objective of the model is to estimate probabilities. So, for example, in the example of ICU patients, if we have a model, we have many variables that can be used as predictors of the outcome, which is whether the patient lives or dies. And the outcome of the model is a probability. We know that this patient's probability of mortality is 43%. And as you know, what that means is that out of 100 patients that look like that have a probability of 43%, if the model is a good model, we expect that 43 patients out of every 100 that look like that will die. And we expect that 57 out of every 100 patients that look like that will live. Now, that doesn't mean that exactly 43 will die. I mean, it could be 44 might die, or 45 might die, or 41 might die. That's not the issue. The issue is that the probability is somehow an accurate representation of what to expect. Now, if the model estimates that the probability is 43%, and yet 85% of patients who have that probability die, then we don't have a very good model. And we call that characteristic of a model its calibration. It's as if to say that on a beautiful sunny day, and we have a thermometer sitting in our yard, and it's, as I say, it's beautiful, it's sunny, the birds are singing, and the thermometer says that it's -3 degrees outside, then we know that this thermometer is not giving us an accurate representation of what the true temperature is. And we call that measure calibration. So we're asking, in the one sense, whether or not the model produces probabilities that are accurate, or another way of saying that, whether the model produces good calibration. So that's what we're going to begin to look at when we look at the goodness of fit of models. And goodness of fit testing is really applicable primarily to a certain type of model that we call predictive models. Now, a predictive model is a model where we do a study, we have collected many potential predictors of the outcome. We don't have any particular favorites. We just study a lot of variables, and then we allow the statistical procedure, the logistic regression procedure, to select from among many predictors the ones that are most statistically significant and do the best job possible in estimating the probability. This is what we call calibration. And again, there's no favorite variables. Every variable has an equal chance of going in the model. What decides whether a variable goes in the model is whether it's a statistically significant variable. Now, on the other hand, there's a whole different type of study that we call a risk factor study. Now, in a risk factor study, we're not so much interested in whether or not the probabilities being produced by the model are correct. What we're interested in is whether or not we can estimate the odds ratio correctly. So, for example, let's suppose that you had this idea to study the association between coffee consumption and bladder cancer. Now, I'm not suggesting for a moment that there is such an association, but let's say that that was the idea of the study. You have a particular risk factor, that's coffee consumption, and you have a particular dependent variable or response variable, and that is bladder cancer. You could almost write the paper without collecting any data. You can write the title. The title would be The Association Between Coffee Consumption and Bladder Cancer. That is clear. You can write that down without ever collecting data. You can even put down shells of the tables you're going to include in the study, and all you have to do is fill it in with the actual data. And then everything about that paper is driven toward understanding the association between a risk factor and an outcome variable. The other variables are not really important except in the sense of how they better help us understand the association of primary interest. So let's say that you got a grant from a drug company, and the grant was to study their new drug in the treatment of a particular type of cancer. So you have this grant that gives you $1 million a year for 1 year to study this phenomenon. You collect a lot of information on patients. And then you have all of your data, which drug the patient got, whether or not they got cured. You also know their age, their sex, their height, all sorts of information about the patient. And then you go through a model building, and then after a year you have a big meeting with the pharmaceutical company to tell them the results of the study. And then you show the first slide, and one of the variables, the most important variable, is not in the model. And the pharmaceutical company representative says, "Why isn't drug in the model?" And you say, "Well, it wasn't statistically significant." That's not good enough. They did the study because they wanted to understand whether drug was significant. So it's not a matter of telling them that it wasn't statistically significant. You had to have that variable in the model. So I call that type of study a risk factor study, because the primary risk factor must be forced into the model. And every other variable that you have is not selected on the basis of whether it's statistically significant or not. It's selected on the basis of whether or not inclusion of that variable in the model affects in a meaningful way the odds ratio between the risk factor and the outcome variable. The risk factor must be in the model. And in that type of study, the probability that they get cancer is not the question. The question is, what is the odds ratio of bladder cancer controlling for potentially other variables? Or is there an effect modifier of that association so that you can look for those interactions and explain the odds ratios within different strata of that other variable? That's what's of interest, not the probability. So I would suggest that in that case, the probability is not the most important issue. What's the issue is odds ratio. And estimating the odds ratio is not a matter of good luck, it's a matter of algebra. We know from what we've done in this course that the odds ratio is algebraically associated with the coefficient in the logistic regression model, so you always can estimate the odds ratio. It's not a matter of whether or not you have good estimates of probability. But good estimates of probability are very important and are very relevant in some situations. For example, let's suppose that this woman was living in San Francisco, and she was beginning to have a lot of difficulty climbing up the steep streets in San Francisco. Every time she would climb up the street, she'd get out of breath, she'd have to stop often. Her family was concerned, "Why can't you go further?" And she said, "You know, I'm just short of breath, I just can't do it." So the family encourages the woman to go see her doctor, and the doctor says, "Listen, I think you should go see a cardiologist," so she does. And when she is in the cardiologist's office, the cardiologist says, "Well, I think we should do some films and see what's going on." And so they do some x-rays, and they find out that she has 2 blocked arteries to her heart, and they recommend that she go through a double bypass surgery, which she agrees to do after he tells her and her family that 97% of patients who have this surgery are back to work normally within 6 weeks, and so she'll do fine, and she agrees and has the operation, and then unfortunately dies in the recovery room. So the question here is, she was given a probability. Does she have, or does her family have the grounds to basically claim that the hospital has somehow has it been malpractice? Have they somehow failed their mother in terms of being able to accurately tell her what her chances were of doing well? And I would suggest that that the hospital really hasn't failed, because they have told her that the probability was 97%. They didn't tell her the probability was 100%. They said 97%. And as you know, a probability of 97% means that 97 out of every 100 patients will do very well, but 3 out of every 100 patients don't do so well. And unfortunately, she was one of those 3. In that case, the estimating of the probability is very important. It's very important to the patient. It was very important to the family. And so giving an accurate representation of probability is very important. And that's what calibration is about. And that's what the tests that we're going to do are about, to be able to determine whether the probabilities produced by the model give you a fair representation of the actual probability of the event. And that's what we call calibration. Now, so the next thing is, do people generally assess the fit of models when they do logistic regression? And I would, so to ask this question, or to try to answer the question, we had one of our graduate students, one of our doctoral students, this was some time ago, go into the American Journal of Public Health and select every single article that appeared in the journal for a period of 4 years. And from this collection of articles, we asked only two questions. Number one, we asked, did the article use the logistic regression procedure? The second question is, if it did use logistic regression, did they make any attempt to assess the calibration of the model or the fit of the model, or whether the probabilities produced by the model were accurate? And the first question was answered by really surprising result that a high percentage of the papers, even in the 1980s, were using logistic regression. If you do a similar study today, you will find that an enormous percentage of papers in the epidemiologic literature, public health literature, use the logistic regression technique. But the second question we asked was, if they did logistic regression, did they make any attempt to try to determine whether the probabilities being produced by the model were accurate? And the answer to that was more discouraging. In fact, we found that a very small percentage of those papers at that time made any attempt to do goodness of fit testing. Now, things have changed over time. We now know that more and more people are aware of goodness of fit tests. We see it more in the literature. So we know that it's being used much more often these days than it used to be used. But in any case, I think it's important that we keep in mind that when we're doing a study that's objective is to estimate a probability, we need to look at the model performance. And we're going to assess model performance in two ways. We're going to look at goodness of fit tests, and we're going to look at the area under the ROC curve, which is a measure of discrimination. So we're going to look at calibration and discrimination. When you do a risk factor study, I would argue that it's not as important to look at goodness of fit. There it's important only that we estimate odds ratios, and you can always do that because that's what the logistic regression model does. So having said those things, I think that we're now ready to have a little break. And so when we come back, we'll begin to develop the ideas of behind goodness of fit testing. So see you soon.